So in the last class, we had talked about the force between two current carrying wires, two parallel current carrying wires, I1 and I2, and if they're separated by distance d, that the magnitude of the magnetic force on either wire is mu 0 I1 I2 over 2 pi d. And you can figure out, using the right-hand rule, that if the currents are in the same direction, it's an attractive force, and if the currents are in opposite directions from each other, it's a repulsive force. And I keep forgetting to write its force per unit length. Okay, so what if we change the situation a little bit and we ask a similar question, but let's say that we have a current carrying wire I1, long current carrying wire I1, and then I2, which is perpendicular. What can we say about the net force on I2? This is not a trivial problem. So let's just say that these two are essentially in the same plane of the page, right? They might be, I mean, obviously these two have to be separated by a little bit. They're two independent wires. And if they're carrying currents, they got to have some insulators. So, but they're approximately in the same plane. We want to know what the net force is. Well, the magnetic field due to I1, right? Whoops, let me draw it in a different color. So if we want to know what the force, magnetic force I1 is that exerts on I2, we see that the magnetic field now varies along the wire I2, right? It varies, it gets smaller as R. So in order to do this problem, we would have to do an integral, right? df equals dl cross b. We would have to take a little dl of I2, and so this would be df on 2 is the current I2 in the magnetic field B1, and B1 varies, and so we would have to integrate along the wire. But we're not going to do that. And I'm going to show you why. We could, but we're not. I'm going to show you why. Because if I were just to ask what is the net force on I2, what I want you to notice is that the magnetic field on I2 on one side due to I1, right? This magnetic field is over here, it's into the board, right? So the magnetic field is into the board, B1. Magnetic field is in B1. And that, right, B1, the second B1 I wrote is smaller than the first B1 because it's farther away from I1. And over here, the magnetic field is out, right? B1. The magnetic field is out of the page. So if this is a symmetrical situation, then whatever the force is on this side is equal, but in the opposite direction to the force on this side. Because look at dl cross b. dl cross b, let's draw the force in orange. dl cross b for the one on sort of the bottom right. It's kind of hard because I drew this all at an angle. dl cross b is in that direction, F1 on 2. And dl cross b for the other one, since I is going in this direction, dl cross b is, draw the force in orange, in this direction, right? F1 on 2. So that's just for those two halves of the wire on either side of I1. And so what's the net force? The net force is equal to 0 because those two forces are going to cancel. But is there a net torque? And the answer is yes, there is a net torque. Well, I don't know how to put that, but is not equal to 0. And what rather than calculating the net torque, because it's an integral, which is not easy to do, and we don't need to do that right now. I just want to look at the concept. Rather than calculating the net torque, let's just ask what if these wires were free to move, what would the wires do? If the wires were free to move, then the wires would line up parallel so that their currents are parallel. That's what that net torque is going to end up doing. And actually what it would do is it would not only line them up parallel, but because it's attractive, it would squish them together. They want to be in the same place. Wait, is that right? That's right. I just had to remind myself that parallel currents are attractive. So while the forces and the motion would be somewhat complicated, in the end, what it's going to do is I2 is going to rotate and get closer to I1 if it was free to move, and they would end up being in the same place. Okay, in doing some examples, let's just go back to the original that we found that the magnitude or the force is per unit length is mu naught I1 I2 over 2 pi d, and just ask how big is that force? Is that an appreciable force? Is it a force that we have to worry about when we're wiring our houses or when we're building a circuit? And so let's just figure out what that, and that is attractive if they're pointing in the same direction, repulsive if they're pointing in opposite directions, etc. Okay, so let's just figure out what the order of magnitude force is. So force per unit length, really. And then we can put in a length, right? Force, the magnitude of force per unit length, we've got 4 pi times 10 to the minus 7 in MKS units. I1 and I2, what are reasonable household currents? Household currents, or let's just take the maximum household currents. If max household current, the max household current is typically about 20 amps. That's what your circuit breakers or fuses. They're usually 10, 15, or 20 amps. So let's just say 20 amps. If you had a 20 amp current going through a wire, I'd be a little worried. That wire would get kind of hot. But anyway, let's go ahead and do 20 amps. So let's just say we have 2 wires in your house. Each are of a magnitude 20 amps. And your wires in the wall, sure, they can get close. And actually, you might have observed that if D is 0, this force is infinite. So there is not really an infinite force. Well, that just tells you really you can't put 2 wires in the same place. D is equal to 0 means that one is in the same place as the other, not that it's next to. The closest that you can get 2 wires is, let's say a couple millimeters, or let's just say, obviously, in reality, you might string 2 wires right next to each other, and with their insulation, maybe they're half a centimeter away from each other. So let's just do, I don't know, let's do a millimeter. So a millimeter is, whoops, I'm writing in highlighter. A millimeter is 2 pi, 10 to the minus 3 meters. Okay, so let's just say two wires, that really the closest we can get them is approximately a millimeter. So the force per unit length is given by this. And plugging in the numbers, I did it in my head, 0.08 newtons. I'm getting 0.08 newtons. So 2 wires carrying the largest current you could really possibly have in your house that are right next to each other, that are millimeter apart, is 0.08 newtons. If we put them, if we could somehow get them a tenth of a millimeter apart, which would be awfully hard, that's still only 0.8 newtons. So the force is not appreciable. I mean, it is measurable, but it's not something we have to worry about. It's not something we have to secure our wires so they don't move. But what's interesting is that that this is something that we have to take into account when we're talking about electromagnets, especially when we're talking about superconducting electromagnets. So this is just an aside. Create really large magnetic fields, and typically the only reason you want to do that I know of is in experimental science, experimental physics, experimental engineering. There's not a whole lot of call for super large magnets, but in studying the properties of materials, it is often useful in medical science also, actually, I got to say. NMR or MRI machines use large magnetic fields. And typically use what's a superconducting electromagnet, so that the wire has no resistance, so that you can put a large current into it without it heating up. One issue, of course, of large currents is wires heating up and melting, but another is this force. Oh, sorry, one thing that I didn't say, force per unit length, 0.08 newtons. So for 1 meter, it's 0.08 newtons. For 2 meters, it's going to be 0.16 newtons. For 3 meters, it's going to be 0.24 newtons, right? We'd have to multiply both sides by L. But, in your house, the longest stretch of 2 wires that are going to be next to each other is, not more than probably 3 meters, right? That's the height of a floor. So it is a larger force when we take into account. I keep on doing that. Ooh, this is Newton per meter. I hope you caught that. This is Newton per meter, 0.08 newtons per meter. So if we have a 3 meter long wire, it's 0.24 newtons. A 10 meter long wire is 0.8 newtons. Okay, so that's force per unit length. I keep on thinking of force and force per unit length as the same thing, but they are not. Okay, so superconducting electromagnets. Get back to superconducting electromagnets. With superconducting electromagnets, we might have much, much larger currents and wires that are much closer together because we're trying to create really large fields. So we're creating coils of wire where we're putting wires super close to each other. Now they're not straight wires; they're coiled wires, but it's going to be the same kind of thing. We will figure out some things about coils later, but just in the order of magnitude. Right, if you change those 20 amps to let's say 100 amps or 200 amps, so let's say 200 amps, if we so that's multiplying it by a factor of 10 and 10, by a factor of 100 if both of them are 200 amps, and then let's say we get them apart by a tenth of a millimeter, which is probably reasonable because it still has to be insulated wire, so you still have to have some insulation. I'm looking at a tenth of a millimeter. Yeah, a tenth of a millimeter. So we've got a factor, that's 10 to the minus 4 on the bottom. So we've got a factor of 1,000, right? 10 on 10 for one current, 10 for another current, and divide by 10 for another, and multiply 10 more for the tenth of a meter on the bottom. So we've got a factor of 1,000. So instead of 0.08 newtons per meter, 1,000 times that, 10 times that's 0.8. It's 80 newtons per meter. So now we've got, right, so, maybe, and I'm just, it's just plugging in some numbers, it's maybe 80 newtons per meter. Now, 80 newtons, if you put this thing in, you wrap the wire and you put it in, let's say, epoxy, which is what you might do, in order to harden it and keep it in place, that's going to hold 80 newtons per meter. And let's say it's, but you wrap in the wire, you got 100 meters of wire, now you've got 8,000 newtons. 8,000 newtons is a relatively large force, right? So for one, and again, we're talking about something slightly more complicated, which is a coil of wire, which is not two parallel wires, but it's the same concept. For 100 meters, therefore, it's 80 times 100, 80 newtons per meter times 100 meters, equals, let me do that again. We've got 8,000 newtons of force between the wires, essentially. 8,000 newtons is a large force, right? I weigh about 700 newtons, so that's about, that's like 1,000 pounds of force. Somewhere in there, 1,000 pounds of force. That's a lot of force. Now that's pretty easy to affix your wires. Again, what you do in order to keep those forces from, because what the force is going to do is it's either going to, be attractive, and actually there's some repulsive forces that you get. So I got to think about. Hold on a second. I guess it's attractive forces. If in a coil, when you coil them up, all those currents are going in the same direction in the coil loops. So I guess it's attractive, so it's not going to push itself apart. Interesting. I'm just thinking. I know I have in the past thought of some examples where the wires are in the opposite direction, so that it would push itself apart. But in any case, you just sort of, if you have these forces and you don't want the wires to move, you would, what's called pot it in epoxy. You would put it in epoxy, pot it in epoxy, and let it set so that there's glue basically holding the wires in place. It's interesting that when you get to really, really esoteric, sort of weird experimental physics, and you get to some super, super large electromagnets, they do have electromagnets that just can't hold themselves together, and because of the magnetic forces, do destroy themselves. But they do create very large magnetic fields before they end up destroying themselves, and those are pretty interesting but really unusual kinds of experiments. And I'm not entirely sure why you need such a large magnetic field. But anyway, we will get to the magnetic field of a coil a bit later.